So let's start with the definition. A set of vectors and let's just call these objects U, and then let's put P of these vectors in our set. So I got P vectors. And all of these vectors will have exactly n entries, so I'll say that's in Rn, is said to be an orthogonal set. So to be an orthogonal set. If each pair, ooh, his marker's almost dead, of distinct vectors from the set is orthogonal. From the set is orthogonal. That is, and here's kind of the shortcut way to think about it. If I take some U1, or sorry, not U1, UI, and take the dot product of UI with some other UJ. So that's basically just some arbitrary item in the list and another arbitrary vector in this list of vectors is equal to 0, because that's what we mean by orthogonal. And we just want to clarify that I don't want to compare the same vector with itself, so I just want I and j to be different. Change of the guard. Okay. Again, these definitions just kind of, there's a lot of words. They don't make as much sense as just doing an example. So, go ahead and follow along here. Let's define an orthogonal set. So let's show that the set of vectors, and we will provide explicit definitions for these in just one moment. So U1, U2, and U3 is an orthogonal set. Is an orthogonal set where U1 is equal to 3, 1, 1. Okay, so it's 3, 1, 1. U2 is equal to minus 1, 2, 1. Minus 1, 2, 1. And the third vector is equal to negative 1/2, minus 2, and 7/2. So the definition of an orthogonal set is basically saying this. I have a list of vectors, and if I'm going to call the entire set an orthogonal one, then the relationship between every single possible combination of the members, they are all orthogonal to each other. Okay, so now in a practical example, I have a list of 3 vectors. So if I want it to be orthogonal, I need every single one of those vectors individually to be orthogonal to every other vector. So here are my combinations, right? I need to check U1 dot U2. What's another combination I'm going to have to check? U1 dot U3. And what's the last one I'm going to have to check?
U2.
Yeah, U2 dot U3. Why am I not concerned about doing, say, like U2 dot U1?
It's the same as U1 dot U2.
Exactly. Our properties from the previous lecture let us know that U2 dot U1 is exactly the same thing as U1 dot U2. So when we check this, we're checking the flip side case. Same for all of these. Okay, and so we did some practice actually computing these dot products. All it's going to be is visually match up the corresponding entries together and multiply them. And then you'll add them up in a linear combination. So with U1 and U2, I'm going to take this first entry 3, and I multiply it with the first entry of U2, and that becomes the first product. And then to go on and continue, I just link those all together with a bunch of plus. Okay, so the next one, I take the second entry of U1, and I'll take the second entry of U2. Put a plus sign, link these together in a linear combination. And then here is my third entry, is a 1. And then over here, my third entry also happens to be 1. Does that make sense? Okay. And so then this ends up being 0. Is that what we want it to be equal to?
Yes.
What does that tell us about these two vectors? They're orthogonal to each other, by definition. Cool. So then, what about u1 dot u3? How would I set this up? What's the first product?
3, negative 1/2.
3 times negative 1/2. And then how do I continue?
1, negative 2.
1 times minus 2, because I'm comparing the middle 2 inches. Then?
Plus 1 times 7/2.
1 times 7/2, right? So I take the third entry, multiply with the third entry. And this, you'll see, minus 3/2. And then you go negative and then to minus 7/2, and that cancels nicely with positive 7/2. Equals 0. Is that what we want?
Yep.
Why?
Orthogonal.
Yeah, because if the dot product is 0, that tells me that they're orthogonal to each other. So then, the last one to check, u2 dot u3. How do I set this up?
Negative 1 times negative 1/2. 2 times negative 2. And then 1 times 7/2.
Very good. And then positive half, we go down by the 8, so that's going to be negative 7/2, and then again cancels with the positive 7/2, we get 0. Okay, so is this every combination of vectors in our set?
Yeah.
When we compare all of them to each other, are they always orthogonal to each other?
Yes.
So every single vector is orthogonal to every other one. So what can I call this set u1, u2, u3? An orthogonal set. Cool. So that's the procedure for showing that. So if you were like on an exam, if you were given like a very similar list of vectors and you were given explicit numbers for them, you're going to want to figure out basically all the different combinations to see how they relate to each other, and then just compute the dot products. Yes?
So it's said to be orthogonal. Yeah, right? Is it pronounced right?
Orthogonal?
Orthogonal. So that means 3 vectors are perpendicular to each other, right?
Mm-hmm.
So I just can't imagine how can they be perpendicular in the plane in the coordinate system?
Yeah, yeah.
How then 3 of them can be perpendicular?
This example happens to be in R3. And what's nice about the definition of orthogonal is that we don't really restrict this to just the spatial dimensions we can visualize. And so that's why the dot product being equal to 0 becomes a really central part of that definition. Because we can no longer rely on visual intuition to verify whether something is a right angle to another thing. Especially when you're dealing with like 7-dimensional space. Okay, well what does that even mean, right? What does it even mean for something to be orthogonal to something in 7-dimensional space? Well, we have no visualization for that, and so we rely on the principle that in general, I need a u dot v being equal to 0. And that's just kind of going to be the universal test, irrespective of what space we're doing, for 2 vectors being orthogonal to each other. Does that help? Okay.
Almost certainly out of the scope of this class, but is there a mathematical equation to determine the maximum number of vectors that can be orthogonal to each other based off the number of dimensions?
Yeah, and by outside the scope of this class, we talk about that theorem in this lecture.
Wow.
Yep. So you're already thinking in the right direction. How many of them we can find, the most amount of information we can squeeze in there. And because it's going to go back to, I'll give you a hint, it'll go back to what we studied about bases.
Okay.
That minimum amount of information to span a space.
Mm-hmm.
Okay, so let's move on. Here's the next little theorem. And actually for your notes, I'm going to label this as specifically example 1.1 for the lecture. That's a terrible numbering system. It's lecture 6.2, so I'll call this example 6.2.1 because we will refer back to this example. So make sure you get that little tag in your notes so if you refer to example 6.2.1 later, you know exactly which example to look back at. Okay, so if S is equal to the set U1, and then we have, again, some list of vectors, so P vectors. If this is an orthogonal set, so we're coming out the gate and just saying that whatever set this is, it's going to have the property demonstrated over here. So we're just declaring that from the get-go. Of non-zero vectors, in Rn, then S is linearly independent. Linearly independent. And hence, is a basis for the subspace spanned by S. Okay, side consequence that's actually just really interesting here. This is a test for linear independence, meaning that, remember in past problems when you were asked to determine whether some vectors were linearly independent or not, we have an even further way to test that. You could have taken the dot, so like if I have some vector A equal to, let's say 2, 4, and I have some vector B is equal to 6, 12, and you're asked to see whether they're linearly independent of each other, well, the first strategy that we had was just row reduction, right? So you would row reduce this and see whether or not you have a pivot in every single column. That's the really time-consuming way. That's the really unfun way. Then we found out a shortcut that if we only have a list of 2 vectors, we can just see if it's possible to scale, like multiply one of them by a scalar multiple to get to another one. So in this case, I actually could do that. I could think about my vector B as just taking my vector A and multiplying it by 3. Okay? So this we would conclude is what? Dependent. And then what this is now telling us is that orthogonal sets of vectors can tell us whether or not it's linear independent. So if I took their dot product now, which is pretty easy to do, A dot B, what's the dot product? Well, I take, again, 2 times 6 plus 4 times 12. And I don't really even need to simplify that to tell you, guess what's not going to be 0? That. That is very not 0. And if it's not 0, they are not orthogonal. And so if they're not orthogonal, they could never form a linearly independent basis. So that's another way to check now from now on. This is sometimes going to be way faster. So for example, way back here, if you had been asked to determine if those vectors were linearly independent of each other, you would have had to do a 3x3 row reduction, all that stuff, and the whole thing, okay? That's not very fun. Compare that to computing bing, bing, bing. That's not difficult. You can achieve an answer much quicker. So that's one immediate kind of benefit of having these orthogonal sets. Does it make sense?
Yeah.
Okay.
Okay, so if the dot product is not 0, therefore it's linearly independent.
Okay, so if the dot product is 0, then what we first conclude is that, is this orthogonal or not?
Orthogonal if it is equal to 0.
Right. If it's not equal to 0,
Oh, it's not.
they are not orthogonal. And if they are not orthogonal, according to this theorem, I need an orthogonal set in order to be linearly independent. So I'm failing to satisfy orthogonal set, so therefore I will fail to be linearly independent. So not linearly independent. Does that make sense now? Cool.
Good job.
So let me put a definition underneath here. An orthogonal basis, for subspace W for subspace W of Rn is a basis 4W, that is also an orthogonal set. Now, I can smell the question, well, didn't we just restate the same thing? Like, doesn't every single basis then an orthogonal basis? Well, not quite, right? Because you can have a basis for a subspace, but all of the vectors in that basis are not necessarily orthogonal to each other. For example, if here's the R2, well, if I have a vector like this, and then a vector like this, that's definitely not orthogonal to each other. That being said, those are definitely linearly independent of each other. And so I could span all of R2 using those vectors. They are not orthogonal. So not every basis is automatically orthogonal. But if I had chosen, say, instead the vectors I hat and j hat, well, those are orthogonal to each other. So then my basis vectors are both orthogonal to each other, and they're spanning all of R2. So that's that added property to be an orthogonal basis specifically. Yes?
I have a question.
Yeah?
If I have vectors 1, 2, and 2, 2, those would be linearly independent, right?
1, 1, and 1, 2?
Yeah. But that's not orthogonal.
Good point. We don't want to immediately assume that the dot product is going to have information, or if the dot product is that them being orthogonal or not is not necessarily going to be an issue of independence or dependence. But the theorem is telling me that if I'm given orthogonal vectors, I can anticipate them being independent.
If they are, okay.
Yeah. So notice that the line of implication is going from start with orthogonal, and the orthogonal thing implies the linear independence.
So if they're orthogonal, they're always. But if not,
Yes.
not always.
Exactly. So we cannot, this is a great example of how you don't want to assume the converse of the statement. The converse of the statement points and says, well, what about linearly independent? If it's linearly independent, does that mean it's orthogonal? Not necessarily. Because like Kyle observed here, those are most definitely linearly independent of each other, but certainly not orthogonal to each other. Okay? So whenever you read a theorem, just keep that in the back of your mind. Don't inadvertently assume that both directions are true. Only believe one direction at a time. The direction that the theorem is giving you. Okay, does that clarify the... Okay. So then there's a fun little way to compute these things. And I'm keeping that example up on the other side intentionally because this example will use the same vectors. Okay, so here's a theorem. And it's going to be a theorem that helps us compute directly solutions to linear equations. Yes?
Okay, cool. So, I'm just trying to make sure, if you have any set of orthogonal basis vectors, if you rotate those vectors, for example, is there, under every single circumstance, do they always stay orthogonal?
So you're saying if you have orthogonal vectors and then you do a rigid transformation of them somehow.
Yeah.
Yeah. So long as it's a rigid transformation. So long as you're rotating and strictly only rotating and not actually shifting and pushing around the vectors themselves.
Okay.
Yep. So if you preserve the structure, they're still going to be orthogonal.
So, is there, comment on this question. So, is there like a list of transformation we can do or can't do for them to still technically be orthogonal?
There is a list. Is it comprehensive to the textbook? No. Are those things that you contextually go case by case and solve for? Yes.
Okay.
Yeah. Great example would be Prem's Rubik's Cube. Okay, the rigid rotation of picking up the Rubik's Cube and then turning it over on its side and setting it back down, it didn't suddenly become like a pentagon, right? All of the sides are still orthogonal to each other, but all I did was make a rigid transformation. And you could describe that rigid transformation in that specific context. But there's no formula. If you're looking for like a general formulaic expression, that doesn't exist, unfortunately. Good? Okay. another set of these U1 to UP, be an orthogonal basis. Be an orthogonal basis. Okay, what does that tell me about those vectors? Well, that tells me that every single one of those vectors is orthogonal to each other and forms a basis for the subspace that it's being. For a subspace, W of Rn. For each y, so now if I take a vector that is in this subspace that I'm spanning, the weights in the linear combination, so if I took y and I want to describe it, I have C1 U1 out to CP UP are given by an actual neat formula. I would argue more efficient than Kramer's rule. Cj is equal to, so we're going to do a ratio of dot products. In the numerator, you do the dot product of y dot u sub j. And in the denominator, you do u sub j and take its dot product with itself. A scalar divided by a scalar is still a scalar, so that's why I'm separating the scalar material in parentheses. And then, well, I mean, I technically don't have to do that. You just know that this is going to produce scalar. And that's going to be true for all of the j's 1 through p. So, this is going to be a really, really efficient algorithm because it's dot products. If I had a system of linear equations, again, you could choose to do it with the typical row reduction, blah, 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 right? And find the solution set. Or, now, if we were able to find an orthogonal basis and had that orthogonal basis, then I could actually directly just do some dot products and actually and solve for each component of the solution vector one by one. So let's do an example of that. I'm going to reuse all of these vectors so you don't have to write down more information, okay? And I will also reproduce this formula in a second so that you don't have to have it memorized. Okay, example. So we have the same exact set, and so what I'll do is I'll kind of do that, we'll continue it. Express the vector y is equal to 6, 1, minus 8 as a linear combination. Of the vectors in X. Okay, what is that really asking me to do? Well, it's asking me to effectively figure out which weights are going to satisfy this equation. The 3, 1, 1, minus 1, 2, 1, minus 1 half, minus 2, 7 halves, times some vector with weights C1, C2, and C3 is equal to the vector 6, 1, minus 8. So this is really what the question is asking. It's asking, give me the solution C here. What must I multiply by these vectors to spit out this? What weights must I pick so that I can tune my set of vectors to be equal to this? And this is what we did all the way back in chapter 1. But instead of having to row reduce, we can utilize this theorem and reframe this into, well, here's my U1, right? Here's my U2, here's my U3. This is my C vector that I'm looking for these guys. And here's my Y vector. And what the formula told us just above was this. The formula is plug and chug. It tells me that Cj, so depending on which entry we're solving for, to find that, all I need to do is take the dot product of the vector y with the corresponding u vector with the index j, and then divide that by the vector uj in dot product with itself. And that dot product is just going to spit out precisely what that entry is. So it's kind of like a faster Cramer's rule, basically. And we can do this. So C1, I'm solving for C1 now. So what is my J?
1.
1. So I'll take Y dot U sub what? U1, divide that by what? U1 dot U1. And that's pretty straightforward. So here's my Y, here's my U1, so this is the vector Y, this is the vector U1, so 6 times 3 is 18, so 6 times 3, 1 times 1, and minus 8 times 1. All over U1 dot U1. So I just go to U1, and that's pretty easy to take with itself. The first entry of itself, and its first entry of itself, its first entry, and its first entry, or third entry with its third entry. Does that make sense? Okay. Because then, when I simplify, then that tells me that C1 is equal to 1. Now in a similar way, we can solve for C2 and C3. So C2, somebody tell me, how will I plug the 2 into the formula here?
Y times U2 over U2 times U2.
Very good. Okay. What about Y dot U2? What does that product look like?
It ends up 6.
So I take the first component, 6
Yeah.
and minus 1.
And then 1 and 2.
I take the second 1 and 2.
And then negative 8 and 1.
Negative 8. And then the third component. All over, and then U2 with itself. So minus 1, 2, 2, and 1, 1. And when you do that one, it simplifies to negative 2. Does that make sense? Okay, something to help you just quickly verify that you know how to do this on your own. See if you can verify for yourself that C3 will also end up being minus 2. Okay. In the meantime, I should probably teach you this thing because this is like actually super important for the next section. Okay. Those of you who've taken Calc 3, this will ironically actually be a little bit more difficult because you have a conception of this concept in your head. So pretend like you don't know that one for a second. And then we're just going to relearn. We're going to generalize. So I'll anchor you with something kind of concrete here. What if I have some sort of a graph? Here's x1, here's x2. So I'm operating at R2. And then I have some vector y. So here's my vector y. And say I have another vector, say it's pointing like this, u. I have some vector u. So far so good, I just have 2 vectors, that's all. Now what I want to do is I want to then think about the span of u. if I want to take the span of U, I'm basically saying I'm going to take all the linear combinations. So I could scale it down this way. I could also scale it up this way indefinitely, right? And so what we can call this, let's call this L, where L is what we are going to use to describe the span of this vector U. And so the span is this whole thing. Okay, now what we're going to do is I want to orthogonally project my vector y onto the span of U. I want to drop it down in a projection. So it's going to come down 90 degrees like this, form a orthogonal projection. I'm dropping it down. And now let's figure out exactly where on the span that intersection is happening with the span and this thing that gets dropped down. And then let's make a new vector that goes all the way up to that point and call this y hat, where y hat will be the symbol we use in this class for the projection onto L, which is the span of U, from the vector y. So Calc 3 people, you're like, okay, well now it's kind of familiar. The primary difference here is linear algebra is accommodating for the span concept. So when U isn't long enough, and you're not technically landing onto U, you're landing on its span in that same direction. And then what we're going to do is we're going to call the difference vector. So this vector that we dropped down, the head is going to start here, and the tail is going to end up there. I said that exactly backwards. So the tail is down here, and the head is going to go up here. And what we're going to do is we're going to call this some z, which is precisely the difference of if I took the vector y and subtracted my y hat, the projection. Now, why do we care about those different components? What we're building toward in Chapter 6 is simply this. Not every system of equations is consistent. And guess what? In most of your engineering projects, the equations that get spit out don't even have solutions. We do not want to go to the populace and say, yeah, sorry, basically we can't build half of the mechanical instruments in the world because there's simply no infinitely precise, technically correct, consistent solutions to anything, right? Because in the real world, we know that about after the third decimal place, stuff kind of stops mattering that much in terms of precision. I mean, it's really remarkable. I think they only needed like 7 or 11 decimal points to get somebody on the moon and then back from Euler's calculations by hand, okay? So there is a really, really limited amount of precision that we technically need. And so what we're building toward is, all right, real talk, we're not going to have, yeah, sorry, question?
No, not a question. Totally useless factoid that will not benefit anyone whatsoever. For the diameter of the solar system, the difference between the 14th and the 15th digit of pi, when calculating the diameter, is a matter of inches.
Yep. So there you go, folks.
3.14 is good enough in most cases.
So, that being said, if you have a system that is inconsistent, so that means you have a system of linear equations, you want it to accomplish something, it's just not going to give you any solutions. What we can do is we start looking for ways to approximate solutions. What's the closest possible thing that is actually satisfying all the equations? I don't know, you all have probably used Excel to do a regression. So you have data points, you did a lab, and you're trying to prove that when you drop the slinky and you're measuring the spring force, that when you took your measurements, did you get a mathematically entirely precise model of how that force is supposed to work? Of course not. That's like the entire premise of science, is that it's not going to be perfect, so you need to know how to study that. The tool is to approximate those solutions, and what your computer is doing to generate those visuals is what we're building toward. Okay, so what we're building toward is the math underneath the software that builds you visual regression models, that builds you approximations of solutions to equations that don't have solutions. Okay, why orthogonality? Why these projections? It's because we find that the most efficient way to figure out the closest possible thing to the solution is the straight line distance between where the solution should be and where we actually are. And so we're going to take a very, very deep interest in being able to break down these vectors into orthogonal components. So now, I don't have to think of my vector y as just this floating y out here in my space. I can think of it as in the explicit sum of two vectors that are definitionally always going to be orthogonal to each other. In this case, my y hat, and this difference, z, the y minus the y hat. Yes?
I have two questions. So from that side of the board, is there, so in determinants, we found out that it doesn't need to just be the top thing with the matrices, we can
Sure,
figure it
right.
out. Is there gonna be like an implication of that in this too, or a way to say like, oh, it would actually be easier to do this line versus this line? Is there a way to think about it that way? Or if you said, if I had these two equations and we need to add one more equation to get three sums, is there a way to use this formula to get the next equation? If you're understanding what I'm saying.
I think I'm following. There is not a perfect analog, but the closest thing to an analog that you're talking about is what we call the Gram-Schmidt method. Well, that's 6.4, I'm pretty sure.
6.4.
So when we get there, that's going to be the closest we get to something like that, where you have freedom to construct those kinds of formulas. For now, does this visual make sense?
No. That's
Okay.
what the second question is about. So pretty much, you're basically saying like, this is the application of this is pretty much, we have a U, but human error means that we can't really put it on the line if we have a Y vector, we need to relate to a U vector. So now we say L span of U so that we can actually put it on there, kinda, sorta.
Okay, very close. So when I was talking about the application to approximating solutions, that's giving you vision for where we're headed in future sections. That's not what this section's about. This section is like, well, you need to have the tools and the language to actually handle that later. But right now we just need to learn the tools. So to motivate taking the time to actually learn these tools, it can be helpful to know exactly why you're going to be needing them in the future. So don't apply the application exactly to this per se. All this is saying is, I have a vector, I want it to lie on the same exact direction as one of these vectors. And sometimes I just need to consider the whole span in order for that to actually make a connection.
So the linear combinations of the weights that you could times U by can lie, that will make a line that you can lie what you want it to lie on?
Mm-hmm. And then that's precisely what we mean by trying to figure out what is my projection vector. Yep. And of course, with all things, there's a formula. And this formula is just as easy as that one. If anything, it's actually going to look basically exactly like this with one small modification. So here's the definition. Let the vector y and the vector u, these are both in the same Rn. And we'll use L as shorthand for the span of the vector u. The orthogonal projection, of the vector y onto L, orthogonal projection of y onto L, denoted, as we have already seen on the picture, with a y hat, or projection PROJ sub L vector y is, and here's the formula, y hat, or I'll list both of those here because they're equivalent, so you could say either one, is equal to y dot u over u dot u times the vector u. Now, what immediately about this is striking in light of the previous formula?
It's almost the same thing.
It is the same thing, right? Like, this is spitting out effectively the coordinate, right? The weight required for this component of the solution. So to solve a system of equations, we have a solution to a system of equations. We're doing the same exact type of thing, and then simply taking that and scaling it the size along there. And that's going to get us really, really close.
Oh, so n is y vector?
Wait, what?
Oh, I'm dumb. That's notation. Never mind. No. I thought that small n by the dot where there's the right angle sign
Oh.
was notation of something else. Might want to erase that from the notes.
Okay, so does the relationship between this thing and then the way we actually have a formula for finding this projection make sense? Fun fact, it's exactly the same thing. Except for now, with the projection, it's a vector, meaning we want the vector multiplied by it in the same direction. So when you actually have to memorize for this, gets minimized pretty fantastically. This, and if you remember this formula to solve the system explicitly, take that same exact structure to generate your scalar weight, and then you have your vector attached to it. Why am I setting this off with parentheses? Again, what's the type of output? Is this dot product going to give me a scalar or a vector? Scalar. What about this dot product? Okay, so if I take a scalar and I divide it by another scalar, that's a scalar. Okay, and that is just going to be a number. That's a vector, though. Okay, and then, so you have some sort of scalar times a vector. Yes?
I got another question.
Okay.
So, how would you like word the like in words, like words?
Oh,
like,
to say like the notation here?
No. Like over there, like what would you use words to explain like 6, 1, -8? Like how would you like say that into like a like if you were to put it on an exam? How would you? 6,
Okay.
1, -8.
If you're asking about like how to verbally talk through like what your math is, because that could be a thing. Like, have you ever been trying to handwrite a math problem and you're like trying to orate what you're saying, and then you start realizing, the thing with the squiggle and the dot and the thing. So the way you can do that for this kind of stuff is whenever you have a column vector, you can just list the entries one by one. So I would say vector y is 6, 1, -8. But for this kind of stuff, you might be thinking, how on earth? If I'm writing this and I'm trying to practice this in my notes, I'd say Cj is equal to y dot uj divided by uj dot uj. So anytime you see a dot product, just use the word dot. And that lets you distinguish mentally between just regular old multiplication and a dot product. They're different things. Over here, this is the one that gets people just going like crazy, because, I mean, that doesn't make any sense. So if you're handwriting this formula, you say, okay, say it with me. Y hat equals the projection onto L from Y. That's how you want to say this. Projection onto L from Y. Or of Y. Doesn't really matter. They're both genitive prepositions. Is equal to y dot u over u dot u times u. That's how you can say those things. So do not call this progeny, okay? or y is equal to proj ly. Okay, so don't be saying that. Get in the habit, because if you actually pronounce and say out loud the English what it means, conceptually this is a piece of cake. Because if you're emphasizing every time you get to this notation that it's the projection onto L of y, now you have that in order. Your brain's kind of cued into, this is what's going on. And then just don't forget that L itself is the span of the u that you're using in your formula. Cool?
That didn't answer my
Question.
Is it always projection onto L? Because that doesn't seem to make it obvious that L is the span of U.
Good
'Cause,
question.
like, what if we have U and V?
Right. Yes. This is because I am not a graphics art design major and cannot produce for you a beautiful 3D rendering of a subspace that I'm dropping something onto, okay? So this is, the L here is kind of that placeholder for, technically, that could be the span of whatever vectors for a whole other different subspace. So you could be projecting something onto a plane. Well, that plane is not just the span of one vector, the plane is a span of two vectors. That's okay. You can still choose to project onto that plane. You would just know implicitly that the vector you're using here is going to be adjusted for that. But that's context by context. So for all intents and purposes, when you're doing just projections between vectors in like Rn, all you're doing is dot product and scale. Okay. How do we feel about that?
Another question.
Yes.
So I kind of didn't answer the question I had, but I'll probably ask you later. So when you technically, if you're going to state it in verbally, you'll need to say y vector and u vector for it can be a scalar. in an equation, or does that actually matter?
So long as you know that y and u are vectors in the same Rn, then you're good to go. Yeah. Because, yeah, I wouldn't need to name these scalars anything special. They, by nature of being a dot product, it is going to be just a scalar. Okay. Okie dokie. I have time to just write this definition so you have it. There isn't much to it past take everything that we've done, and then all we're going to do is say, what if now I have an orthogonal set, okay? So that means I have a set of vectors where all of the vectors inside of my set are orthogonal to each other. Now in that case, what happens if I just take every single one of those vectors and choose to shrink them down or scale them up if need be, to just be uniformly all length 1? So I just have a bunch of little tots that are all length 1, that are all orthogonal to each other, okay? We have a name for that. A set U1, UC is an orthonormal set. If it is an orthogonal set, is an orthogonal set of unit vectors. Unit vectors, that's kind of the important thing here. They all have length 1. And if W is the subspace, spanned by such a set, then this is my set of vectors here. My set of unit vectors that are all orthogonal to each other is an orthonormal basis. Orthonormal basis for that subspace W. Okay, so basically, here's the checklist. Are all of the vectors orthogonally to each other? If the answer to that is yes, then go further. Is the length of every single one of those vectors been scaled to be 1? If the answer to that is also yes, we can call that orthonormal now. So whenever you see your problem talking about orthonormal stuff or orthonormal bases, all that means is, okay, you got a set of vectors. If it happens to be basis, fantastic. They all have been shrunk or scaled to be just exactly length 1 for ease of calculation. Cool? Alrighty, any last questions?
I believe they said this explanation, all possible forms of orthonormal basis, basically all forms of rotation. Rotated unit vectors.
If the rotation doesn't change the orthogonality of any of the vectors. You could. So like say I have something that's orthogonal and I have a transformation that rotates but then also pinches. Well, if I do a rotation and they are no longer orthogonal to each other, that's not going to work. So as long as I have a rigid transformation that preserves that.
Okay.
They need to be rotated exactly the same way.